Pencast number 9. It's problem 9.35 from Griffiths. We're given this electric field, um, E and M wave, or just the electro wave, we'll call it, with U defined to be kr minus omega t and omega over k equals c. Part A is to confirm that this works for all the Maxwell's equations in free space. Just as a note, rho equals 0 and j equals 0 in free space for electromagnetic waves. So we can start from there. We're going to have the first one is we need to show that del dot E equals rho over epsilon naught, but since rho is 0, we just need to show it equals 0. So del dot E, we can see this in the front of the book. It's just going to be the component 1 over r sine theta partial with respect to phi of E phi, or the entire part right here. Make that look more like a phi. So none of this in here has any determinants. There's no phi determinants in this right here. So the partial of E of phi with respect to phi is just 0. So this does equal 0. So there's the first one. And then for the second one, we need to show that del cross E equals the negative partial of B with respect to T. What we're going to get from this is actually magnetic field, and we're going to show that the magnetic field follows the other two Maxwell's equations, which will prove this one. So del cross E, I'm not going to work it all out because it takes a long time and I have a finite amount of space on my phone. So this del cross E is going to give us 2 cosine theta times A over r squared cosine of u minus 1 over kr sine of u in the r hat direction plus a sine theta over r k sine of u plus 1 over r cosine of u minus 1 over kr squared sine of u in the theta hat direction, which should equal the negative partial of b with respect to t. Then we can just take the negative integral of this with respect to t to get what our B field should look like. So B should look like 2a cosine theta over omega r squared sine of u plus 1 over kr cosine of u in the r hat direction plus a sine theta over omega r negative k cosine u plus 1 over r sine u plus 1 over k r squared cosine u in the theta hat direction. So if del cross E is to be confirmed, we need to show that this B field works for the other two Maxwell's equations. So the first one is we have del dot B equals 0. Del dot B, we have 1 over r squared partial with respect to r squared, the r component, plus 1 over r sine theta, partial with respect to theta, sine theta, b theta. Once again, I'm not going to go through the math because this is just math right now, not physics, and I have a finite amount of time, so this does in fact equal 0. I'm not going to go through and show it though, but trust me, it does. Then del cross B needs to be equal to 1 over c squared partial of E with respect to t. So starting with del cross B, once again, I'm not going to go through it all, but it equals k over omega a sine theta over r k sine of u plus 1 over r cosine of u. in the phi hat direction, where k over omega is, or omega over k was defined to be c, so we can just write this as 1 over c and put the c down here. And then the 1 over c squared partial of e with respect to t with the e that we are given gives us a sine theta over cr k sine u plus 1 over r cosine u in the phi hat direction. These two are the same, so these two are equal, and that confirms the fourth Maxwell equation and finishes off confirming all the Maxwell's equations in free space. Part B, we start by having to find the pointing vector. The pointing vector is 1 over mu naught E cross with B. So after taking this cross product, once again, not going to go through it all, but the final answer is 1a squared sine theta mu naught omega r squared 2 cosine theta over r 1 over k r squared cosine squared u minus sine squared u plus sine u cosine u. Jesus Christ, Griffiths. This is not simple. K squared r squared in the theta hat direction minus sine theta 1 over k r squared. I wish I was back in physics 1. Cosine squared u minus sine squared u plus 1 over r plus 1 over k squared r. This should never be an expression. 1 over k squared r cubed sine u cosine u minus k cosine squared u in the r hat direction. That is a mouthful. Who does this? All right. Now, then we're asked to find the intensity, which is the average value of s pointing vector. So the good thing is we can first take some integrals and find that sine squared, the average value of sine squared u is 1/2. The average value of cosine squared u is also 1/2. And the average value of sine u cosine u equals 0. So then when we go and find I, we see we have here a cosine squared u and a sine squared u term. These are both the average value equals 1/2, so this part goes to 0. And the average value of sine u cosine u is 0 as well, so the entire theta term goes away. As for the r term, once again, average value of cosine squared minus average value of sine squared, 0. Average value of sine u cosine u, 0. And the average value of cosine squared is 1/2. So all we have left is a squared sine theta over mu naught omega r squared times k over 2 sine theta in the r hat direction, or for the final answer for part B, I equals a squared sine squared theta over 2 mu naught omega r squared c, since omega over k over omega is 1 over c in the r hat direction. And I'm just going to flip to the other page because I don't want to use another sheet of paper. For part C, power, no, that's not an equals, integral of I dot dA, and this is the last thing we have to find. So we have a squared sine squared theta over 2 mu naught cr squared and the r hat. And then since dA is always perpendicular or orthogonal to normal to the surface, and since this is a sphere, we're in spherical, we're going to have r squared sine theta d theta d phi dr and the r hat, since the r hat's the only one normal to the surface. So these are in the same direction. So we end up with integral from 0 to pi, integral from 0 to 2 pi, a squared sine cubed theta over 2 mu naught c d phi d theta. And after doing all these integrals, we get that the power is equal to 4 pi a squared over 3 mu naught c. And that's the final answer.